also I'll quickly take the roll as well. So no, we've got no Layla, Tamara, and Jake, James, no Flynn, Melanie, Tran, Charlie, Ian, it's not in, Holly, not in, Bull, in, Philip, not in, Abdullah, Anthony, Nicholas is not in, Luke is in, Graham is not in yet, Joanne, Iona is in, Mitchell, and Yin. Great. So also, yeah, another thing to add, today's session is the last session before holidays, in case some of you weren't aware of that. And also, today is the last day to get your assignment 1C in. Is everybody fairly well on track with that? I've had a, no, you're not? Have you sent me some information?
No.
Yeah. It's important that you get onto that. And yeah, so it has to be submitted by 5 o'clock today. Now, today. Today. Oh, sorry. Oh no, 5 o'clock tomorrow. We're on Thursday today. Yeah, sorry. Yeah. Whoop. sorry for the heart attacks. Yeah. Sorry. No. So 5 o'clock tomorrow. It was pointed out to me that the actual date, the cut-off time on Moodle was 11:54 or 11:55 or something like that at night. But
yeah, one question you said today, the last lecture. So classes will not be there for next 2 weeks?
So classes will not be there for the next 2 weeks.
Okay, so by when we have to come again?
So the week starting the 30th. So it'll be
29 means 12, 19, 26. You will be coming 2nd of May, 3rd of May.
3rd of May, I think it will be. Yeah. Sorry, assignment due tomorrow, 5 o'clock. Yeah, it's a relatively small assignment. I'm not that keen to drag that out, folks. You should be all fairly happy with that. But there is also the 3rd assignment, which I hope to release very soon. So now that you got this first one out of the way, I'll release that 3rd one. For any of you who are pretty keen, you can have a look at that over the holidays and think about what you want to be doing for that. We just had to meet a whole bunch of compliance and make sure lots of boxes are ticked and everything with all the assessments. So unfortunately this semester it is a bit of a drip feed, but you also have the site visit assignment to be getting done as well. Was that part B, which has already been introduced to you guys. So we've got that, but then the major research assignment will be released fairly soon. So the predominant use of concrete within architecture, within construction, is as a structural component, and it's been a very important structural component for a very long time. There's a very long history of the use of concrete, and it is actually quite, I guess, an important ongoing field of research into how to make concrete better, how to make it perform in various different scenarios. So on the top right-hand corner there, or the two top tiles there, you'll see, well, possibly some of you will be familiar with such images if you've visited Europe. In many places you can't put down a shovel without hitting a Roman ruin, and part of that has to do with the fact that they used concrete. It's a very, very durable material that stays long after a civilization has met its demise. Bottom left-hand tile, just a bit of comic relief, basically, but not too dissimilar or not too, I say, unfamiliar scene. Also for those people who have been to any older medieval built cities in Europe before the advent of raft slabs, etc. A lot of the buildings there suffer significant movement. It's a fairly interesting one. Bottom right-hand side, not sure where that happens or so. So for your concrete slab design, you will require the input of an engineer, and that will be a structural engineer. And it's also not just any structural engineer. Your structural engineer will have to have insurance relating to the design of footings. So I think Abdullah, where you work, Gino, that's what you do. You guys would have insurance for doing that, but not every structural engineer wants to take on the design of footings. And the reason not every structural engineer wants to take on the design of footings is because it's a relatively high risk area of engineering. If things are designed poorly or incorrectly in regards to footings, it is an incredibly expensive scenario to rectify predominantly. So that engineer may compile the footing report, footing inspections, inspection of trenches, footing and footing steel. Can anybody think of why an engineer would want to inspect trenches and footing steel?
Yeah,
Abdullah,
they are checking that whether the depths of the footing at the time of foundation are accurate, width is accurate, and they also check like the fill depth. If it is more than 400, then we need to apply double mesh.
Yes.
And the slab thickness should be more thickened slab.
Yes.
This is the reason.
Yeah. So a fairly typical thing is like a little bit sidetracked there, but typical thing we'll have a 100mm slab, and then we'll increase that slab to 130mm if we've got loose fill of more than 400mm depth under a site. That's fairly typical. So yes, the engineer will want to ensure that the beams are the right size, that the accommodations excavated in the ground are the right size, because you can't go and do that afterwards. It's not very well a retrospective activity, and so if there are issues with footings later on, it's very hard to determine that. They also so they do floor slab design. They also may take on the roof truss design, etc. And also, if you have a retaining wall over 1 metre high, you need to employ an engineer for designing that retaining wall as well. Typically, an engineer will like to establish the worst case situation and design the building elements to resist that loading. So they'll go, okay, this is our soil movement, this is the maximum possible of our soil movement given the maximum exposure to moisture. We'll design for that scenario. So we've talked a little bit about loads and forces, but in the design of footings, that's very applicable. Typically, when we talk about loads on buildings, we're looking at two contrasting categories of those loads. We've got dead loads and live loads. The dead loads are all the built-in and expected loads. So things such as wall, floor, roof elements, parts of the building, air conditioning, and hot water units. So that's what we design for. We know that those loads are going to be imposed on the building as part of the building structure or services. Live loads are loads due to occupancy of the building, people, furniture, vehicles, etc. We also design for those loads, but we have to anticipate what that is going to be. Now, typically, those anticipations are taken care of in the Australian standards. So if we use the timber framing code and it's sizing up members such as floor joists, they have designed within their sizing of those floor joists an anticipated use of the building. So what type of live loads we're going to have on those floor joists. Beyond, well, not beyond our control as designers, but certainly something we have to accommodate for, but beyond, I guess, the control of the occupants who use the building, are things such as wind loads. So within areas we can be relatively sure of what type of wind loads are going to act upon a building throughout its lifetime, and we segment the continent of Australia into cyclonic and non-cyclonic areas. So if we're building in a cyclonic area, we have to increase our tie downs significantly and increase the loading for wind loads significantly. Within South Australia, we don't have to do that. We have had some freakish events. We had an event a couple of years ago it was just a little sort of isolated, I don't know whether you call it cyclone or tornado, I don't know what the correct terminology is here, but a very big whirlwind out near Blythe that ripped a roof off a church and deposited it on another building, etc. We get that every now and again, but they are some fairly rare events, and we shouldn't always design for such odd and isolated events. Other loads, thermal loads, earthquake and snow loads. So also within South Australia, we don't have a great deal of earthquake load. It's very rare that we'll have any, or it's rare that we have seismic activity, and when we do have seismic activity, it's very, very slight. At the engineering firm I worked with, we did have a bit of a spike or a run on places that, or people who make claims to insurance for damage during the minor earthquake events that we had. But typically these are buildings which are already under stress from ground movement, etc., that happen to open up with that small amount of seismic activity it's part of the process, but the main contributing factor is still the ground movement there. When we talk about loads on buildings, we talk typically in kilonewtons because we're talking about very large forces. So our loads are measured in newtons, named after the physicist, but we talk about them in kilonewtons. So force is a push-pull action that tends to produce motion, tension, or compression. Forces in buildings are referred to as loads. So in this class, I've referred to compression and tension previously. Have I not? No, not a great deal. No, because I teach this class, 3 times. I've got the Cert 4s and the diplomas. It gets a little bit confusing as to how much I've covered some of these aspects. But so as an introduction, a compressive force acts on a body, tends to shorten a body or push parts together. So this column over here, that's supporting floor slab, and then is it supporting another? No, so it's supporting a floor slab, but then we've also got our sawtooth roof with all our trusses ending on beams which load directly over these columns. So this column has a lot of gravity pulling that up, a lot of weight of material, and so it puts this column in compression. So the weight of those materials, well, combined with the forces of gravity, are pushing all those concrete components together. The tensile force is acts on a body such that it tends to lengthen it or tries to pull a body apart. There's not a great, well, there are some things we can obviously see that are in tension around here. Can anybody see? So we've got some cable trays up here. Oh, actually no, the cable trays are not very well suspended, but we've got some hot water pipes running through here, some insulated pipes, and they're sitting on these hangers, which are suspended from rods fixed into the ceiling. Those rods are under tension. So the weight of those pipes pulling on those hangers and pulling on the suspension rods are putting those rods into tension. Now that's not a great deal of tension, because we're not dealing with a great deal of load. But typically when we talk about building structural elements, there are sections that do come under a lot of tension. So one example of that will be, out here we have a fabricated steel column. So those are hot rolled I-beams, and they're welded together with, I guess, what looks to be about 90 by 90 equal angle to make a structure which works, which is tied together. So two I-beams tied together with equal angle webbing. If there is a massive wind on the side of this building trying to push this building sideways, this column, so the wind is coming from the south, this column on the windward side, on the southern side, will be under tension. The column on the northern side will be under compression as that wind tries to bend that column over. It's pulling on one side and pushing on the other. And if we were to look around this building and think about a wind load on the building, we could see that compression and tension, well, the evidence of that compression and tension everywhere. So even in the mullions of our windows or in this column here. So if we try to push that over, this face here would be in compression, the other side would be in tension. A shear force is, I guess, essentially it's where we start getting opposing forces very close together. So if we have something tall like a tree and it's copying a lot of wind from its branches at the top, there's not a great deal of shear happening there because the force is spread out and a lot of the force is happening at the top, and it's just bending that tree, putting it in compression and tension. But a shear force is if we were to get, say, so on our tree with our bulldozer blade close to the ground to push that tree over, we are putting a force directly next to where that tree is retained, and there's the possibility of shearing that tree off. So a good way to think about that is think about the scissors. So scissors in some applications are referred to as shears. So in sewing, so that's where we get the term sheep shearing from. It's from those two blades that act right next to each other to put opposing forces directly next to each other to slice through something. And the same thing happens with buildings as well. So I'll just quickly get a marker. So here's our building here like this, a very simple building. Let's say I get some subsidence happening here. So we've got a bunch of sand or something like that that's gotten wet, but then right next to that, a very extreme example, I've got some expansive clay, some clay that takes up moisture and wants to swell when it gets wet. We get force going down and the force going up very close to each other. When we have such forces like that, we get almost vertical cracking happening like this. Not to be confused with the vertical cracking you get from simple subsidence, because if we have an element which is simply subsiding, and this is, let's say this is an addition which was tacked on in the 1930s, and that's the original part of the house, built, 1905 or whatever, we typically get cracks that get wider and wider. That's a very extreme example, but when we get some subsidence, we get cracks which widen at the top. But if we get vertical cracks which are staying basically the same sort of thickness but going relatively straight up, we know that there's a shear force happening. There's a concentration of opposite forces happening close together. So it's not too common on buildings around Adelaide. Probably a lot of the cracking you would have noticed happens in this fashion, sort of stepped cracking. People notice that. That's where we get, it might be typically it's swelling of soil here, and then the parting of a building in that fashion. don't get too much subsidence throughout Adelaide. So that's our shearing. And deflection. Deflection is not actually a force, but it's a way in which we see forces becoming evident. So it's displacement away from a straight line. So a beam under load will just displace vertically. Typically, our displacements or our deflection within buildings is very minimal, and it's designed to be very minimal. So we're typically measuring that in millimetres, so very small increments. And the main reason we want to keep deflection to an absolute minimum, well, there's a couple reasons. First is that it's very unsightly. If you were to see, a major beam in this building that's under load and it's visibly deflecting, you'd think, oh, that's some very poor design, some very poor architecture. Also, when we get elements deflecting, it places pressure on other things that we don't want pressure placed on. So, such as the heads of our windows. If we had a beam across there with very little clearance above our windows, and that beam started to deflect, it would just transfer that load straight into the windows. The windows would crack, or worst case scenario, pop out and fall down. So we design to minimise deflection for those two main reasons. Typically, when we're talking about materials that act very well in tension, we can actually get away with a great deal of deflection before we get any form of structural failure. But we don't design for that, for those two reasons. Some important definitions and some terminology which is often used interchangeably and incorrectly is foundation and footing. So as written up there, foundation is the rock or soil found in its natural state on a building site. Yeah, fairly well. Although I'd like to add to that definition the rock or soil that underlies a building once the building is built, because we typically modify the foundation of a building, and we may bring in soil, compacted rubble, etc. to improve that foundation. The footing is the lowest element of the structure in contact with the ground, and that distributes the load or the total load of the building. So our footings could be a raft slab on the ground, like we see on that bottom photograph, or it could be stumps that we impose some load onto. So yeah, different types of footings: integrated raft, slab, pier and beam. Continuous footings, strip and beam. So our continuous footings, that's the type of footings you would have seen in a lot of the older symmetrical cottages, the stone cottages around the inner areas, inner suburbs of Adelaide, the Unley Park side, through there, North Adelaide, etc. That's part of the reason why a lot of those buildings also crack, is because the strip footing is not nearly as strong as the integrated raft slab. Also, we have isolated footings such as pads and piers. So the foundation, that being the soil, is incredibly important to understand when designing footings, because we want to know not only what that soil is going to do in certain scenarios, given moisture, but what layers of that soil will do what as well. We classify it into some main categories. So soil types are stable, they exhibit little movement and provide a stable base. Now if we're lucky, we have a stable soil. There's not a great deal of that within the Adelaide Plain. What we do have a lot of within the Adelaide Plain are reactive soils, so reacts with moisture, swells as moisture content increases and shrinks as it dries out. So I think probably all of you would have seen at some point in time, typically if you've been around the racecourse area of Adelaide, but you'll see it in some highly clay areas where you know, right now, this time of year, because it's such a dry year and an extended summer, you see some really wide cracks opening up in the ground. Has anybody seen any of that in places? If you head through the sort of the non-watered parts of the Adelaide parklands and outside of the racecourse and so on, you get to see some large cracks up in the ground there at the moment. Also, further down south, we've got large cracks opening up in a place there. So that's our typical reactive soil. We also have some soft, highly compressible soils that are unable to support loads. They are located down around the Port Adelaide region, where we have sort of not peat but black deposited soils with a great deal of organic matter. They're fairly compressible. We don't have a great deal of that, but there's some places around the world that do. Places like Amsterdam in the Netherlands or Venice in Italy, where it's reclaimed land, they do have a lot of compressible soils. There's also collapsing soils. So they are soils that when you add moisture, they shrink and they settle, and they withdraw their support for the building. So they're silts and sands, typically deposited sands. So sands that have been deposited by wind. And the simple reason they collapse when you add moisture is because with our sand particles we get all sorts of crazy shapes, you know, like this or so, or you know, I don't know, some kind of really lumpy bits, and they will get deposited and they'll sit in a fashion that allows still a decent amount of air between them. You add water to that, it lubricates the sand particles and helps carry them, and they start sitting together a little bit closer. When we get those sand particles sitting closer together, we get the soil shrinking, typically under load. It's not something that we see too much in South Australia, but I saw it at a building in Renmark. They had a broken downpipe there, whole lot of water soaking in one side of the building, and that soil starting to collapse as a result of that. So we do have it about the place, but typically not on the Adelaide plain. So, soil and construction reports. Council require a report before approval is issued. There are two types of reports. Preliminary, so that's simply for the client to decide on the site or possibly the siting of the building within a site. So identify footing type suitable for construction, used as pre-sale information, not used in construction. So it's just indicative information. The other far more detailed report is the construction report. So that details the footing type, details the site works. To do that, or to arrive at that, we use the bore logs. We'll draw up a contour plan, provide cut and fill information, and also some paving advice. Can anybody think why we would include paving advice in a footings report? Yeah, exactly. So, because we're typically dealing with reactive soils that will swell with moisture, if we introduce paving all around the house, we move all the moisture that comes close to the house is moved away from the house and sent elsewhere. So that will dictate the degree of footings that we'll need to design. So that's a way of, I guess, decreasing the expense in footings, and hopefully we'll gain, I guess, some appreciation for expensive footings within our class exercise.
Usually paving, they make it instead of 900 millimeters, 0.9 meters. Yeah. So, in terms of paving advice, do you receive paving advice for the majority of your jobs, or specify for all of them? You need to make 900.
Yeah.
You have to provide 900 meter all around the building for the paving.
Yeah.
It's minimum required.
Yeah. A minimum requirement of your office or minimum requirement?
It's general standards, like
Yes,
every council
yes,
they require
yeah.
900
Yes.
for the paving
Yes.
on all the structure.
Yeah. 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 So yeah, the engineer will detail the footing type, the site works. So the site works, that's in relation to the cut and fill. So I don't have my razors over there. So cut and fill information is important, particularly if we're going to be working on a hill like this. One option is to do isolated footings, so some piers or so, and then do the house on that. Typically, hills face zone. Well, hills face zone is an incredibly restrictive zone. So this area in the hills here, typically zoning doesn't allow for that, and there are some issues around that. So so you'll see in your planning information statements such as houses are to be sited in a way that provides little visual impact, that the building structures are nestled into the landscape, etc. So what the council sort of mean by that is that, and then house nestled in there. Sometimes when we do cut and fill, you deposit the soil on the low side of your cut, but that has hairs on it, or that has some issues with it. One of the issues is with retention of this soil, and also shrinkage and collapsing of that soil over time as well. So the engineer will want to know about the depth of that fill, and to accommodate that, they might engineer some concrete piers that go in there that have a footing, so so you can build your house out to there, for example. Although that last example there I gave of building on that filled portion, councils typically don't like that too much as well, particularly not in the hill space zone. One, because it sort of puts the building out further from the hill and makes it more prominent, but also because of the issues with the subsidence of that fill. Does everybody know what I mean when I say contour plan? Yeah, everybody's seen contour plans before, and if you're going to do surveying, you get to produce those contour plans. Cut and fill information, well, that's just information relating to that diagram I showed just there. Typically that is shown on a contour plan, so you have a plan with lots of contours, and then you show where you're going to be cutting the soil from, where you're going to be depositing the soil from, and the new levels that will result. One thing we haven't covered is a bore log. Does anybody in here know what a bore log is? But apart from you, You do?
That's where they drill down, however, I don't know what the strict depth is.
Yeah.
And they bring that soil up and they record what the soil type is like throughout what they've brought up.
Yeah, no, that is a very good description of a bore log. So the bore is, yes, that drilling down through, or the pushing of a tube down to collect soil, and then all that information is logged. So that's what's being done there. So that's the soil sampling component of that. So this is a particularly large diameter soil sample. A lot of your soil samples come in a diameter of like 30 mil or something like that. Phil, do you know what the actual size of the push tube?
This is, I know that they dig it to the 4 meters down.
Yes.
I don't know what is the bore.
Yeah. Yeah. So, but this is kind of indicative of what you will get. So the soil samplers that go around doing residential work, they have like, it's about 30 millimeter core of soil, and they pull the tubes out, and they have got these core flute boxes with all these segments in it, and they just tap the soil out into that. So you just get these long lines of soil that the engineer can have a look at. and then they make their determination on what type of soil it is, how it will react to moisture, or how it will react in various different situations, whether it's compressible or not. So methods of sampling: hollow spiral drill, push tube, and impact tube. So a lot of your soil sampling will be push tube, and that's just quite simple. There's a few of these setups getting about, like it's a hydraulically driven tube, push tube on the back of a Land Cruiser, and so they can get into a lot of hard to reach areas and sample the soil down to 4 metres or 4.5 metres, depending on what the engineer specified. Impact tube, well, that's when you've got a tube which is, rather than just pushed down by a hydraulic motor, it's whacked from the top, and you can get very small impact tubes. We had a soil sampler do a sample within a house, so within the hallway of a house, take up some boards and ram a tube down with a two-stroke motor, keep joining the tubes together, and then set up a tripod with a winch and winch that tube back up. So you can get soil samples done in all sorts of places with some of that technology. So what we're looking for in the soil sampling is, well, partly determination of these classifications. We want to know whether it's stable, moderately reactive, highly reactive, or extremely reactive. And we will typically get a sample of soil where we've got some moderately reactive, extremely reactive, and then stable at the base where it's weathered rock or something like that. But we also want to know the Y values. So the Y values will tell us how much that soil is expected to increase in size given exposure or thorough exposure to moisture. So given any bad moisture events throughout the life of the building, how much we can expect that soil to swell. So here's a soil sample or a bore log for a place in Clarendon. Now, Abdullah mentioned at their office, they'll take soil samples down to 4 metres. That's also what we would do as well. You notice in this bore log, well, actually, can anybody tell me how deep their soil samples went? But not you, Abdullah, somebody else. Is anybody able to see on that how deep the soil samples went to?
3 metres.
Yeah, 3 metres. Yeah. So that's our final value there. So these numbers here, they relate to the depth of our various different soil profiles. And then we've got hole 1, hole 2, and hole 3. So just indicatively, this is our site here, like this. They're wanting to build a house on that portion there, like that. So they'll go, well, we want to have some soil samples done around that area. So we'll do a hole here, and they'll mark it like that. Do another hole here, mark it like that, and another hole there, mark it like that. Typically, you will also have at least 4 samples done for a house, and then if you're going to have a septic system, get another one done there where you expect to do the septic soakage as well, if you're going for a soakage type system. So that's the standard marker for boreholes, although it's sort of blackened on those 2 triangles like that. Is that a fairly familiar marker to you guys? You've seen that sort of marker before? So yeah, it's a call out for information for a few things. And then you have, say, BH1, like that. That'll relate to, so anybody reading this plan, they'll scale off, okay, 2 metres from here, 3 metres from here, that's our location of borehole 1. And that's all recorded there like that. And so anybody reading this bore log, they can go, oh yes, borehole number 1, it had these layers of soil in it, these were the characteristics, and that's where that soil was on the site. So just looking at borehole 1, we have, or what we have broken down here are various different soil types. So the engineer has had a look at the soil samples and gone, okay, this is a distinct type to that one, and that one, and that one. So they've worked out, okay, these portions are significantly different. So with all of our holes, we've got a horizon down to around 400 or 350. That's our topsoil. That's the lovely soil for growing stuff in. So so that's 400 mil. That's reasonably deep. That's fairly good. And then hole number one, it doesn't. So their second horizon of soil starts at 400 millimeters and ends at 700 millimeters. So there's another horizon, straight under that topsoil, there's another horizon of 300 millimeters deep, and that's silty, gravelly clay, brown, mottled yellow, medium to high plasticity. Gravel is variably weathered silt stone. So not extremely reactive. I imagine we've got some estimated inputs here of 0.02. And yeah, so they haven't actually given their Y values for each of those, but they've given total Ys down the base. But then, so that's only 300 millimeters deep, and then the next horizon starts at that 700 millimeters and ends at 2.2 meters. So that's a very deep horizon. So there's a lot of this soil, which is brown and grey, brown, mottled yellow, high plasticity, few pockets of variably weathered siltstone, and then the next horizon starts at 2.2 meters and ends where the borehole ended at 3 meters. So brown, dark grey, brown, medium to high plasticity. So relatively, how I say it, relatively similar soils throughout that sample. And we're getting Y values of 54, 56 and 65. So it's a little bit over, just a bit over your moderately reactive soil. So we're, or pretty much medium. So your extremely reactive soil, that's Y values of around 100. That's really proper stuff. With our Y values here, does anybody see a structural impact from those Y values beyond the fact that they're just sort of that bit more than moderately reactive? One of our impacts that we can see here is we've got a Y value of 54, one of 56. They're very similar to each other. So in an event where there's a lot of soil moisture, those two are going to swell to the same extent. This one here is at 65. Now we're only talking 10 millimetre difference in Y values. It's really not very much, and particularly if we're spreading out over a large area. That we'll see from our site plan. But there is this section, this borehole here is more reactive than the other ones. And that is also a factor that engineers want to know about in the design of the footings as well. So yes, if the Y values are very high, it's an issue. But if we have Y values which are extremely low and extremely high right next to each other, that is a major issue. Because then we get that sort of thing happening, that shear, that concentration of opposing forces in a very short distance. So our various different slab options, once we've determined what our soil is like and what we want to do, we can start considering some options. So one option is slab on ground, and by and large that's the most common option. Another is pier and slab, another is pier and beam, waffle pod, rillage raft and strip footings. So each of these slab types have different characteristics and behave differently in different scenarios, and that's why we would use them for different scenarios. So our slab on ground, like our tile here or our photograph here, that's designed to carry the whole weight of the building, and the soil can do whatever it wants within limits underneath, and that footing will lift the building and move around to keep that building square and stable. So all your doors are going to continue to open and close nicely no matter what's happening with the soil underneath. So such a slab requires a lot of concrete. We pour a lot of concrete into that to make that a very strong, stable base. A pier and slab, that's this is a pier and slab here, but that's what I'll also refer to that as the waffle pod, and I'll talk about that soon as well. But a pier and slab, that's where we have a concrete slab. Actually, well, what we're in right now is a good example of pier and slab. We've got concrete piers, or I called them columns before, but piers, columns, interchangeable, and then we have concrete slab floors. We can also do that as a ground floor. We can have our soil like that, our slab on the top of that, and our piers underneath that slab. I mentioned the soft compressible soils earlier on, in regards to just around Port Adelaide, etc. That's probably not a bad solution for such an application, particularly if we've got a fairly stable band of soil down there, and then all this is our collapsible soil there. That enables us to lock our slab in with something which is far more stable down lower, and then provide a stable base for our house and have a concrete floor. We also typically use or end up with a pier and slab building where we do big sheds as well. This is digressing just a little bit, but our big sheds typically have large steel portal frames. So everybody's seen those sort of frames before, that scenario. So it might be just your cold rolled C sections, or some of your major universal beams put together to produce portal frames. But those portal frames, they will be locked into some concrete piers, which will typically go all the way up to the base of our portal frames. And then when that building is in place, you cast the floor slab in there, and you have a resultant pier and slab as well from that. Pier and beam, that's typically doesn't relate too much to concrete. So our most common form of pier and beam is with timber. So we'll have timber stumps, and then our bearers going across the timber stumps, and our floor joists going on the top. That's a pier and beam. But this is a scenario. So we've got a we call it a bridge happening there, whereby we have beams supporting that bridge and then piers underneath that beam. A waffle pod is whereby we don't excavate standard beams in a slab. Instead, we put down large square styrofoam boxes and then pour the concrete over top of those. And what we end up having is a concrete structure not too dissimilar to that. If we were to burrow under and have a look from underneath, that would be our structure underneath. That's what it appears as. So that has its limitations for reactivity in soil. So it was designed in South Australia, but not a huge amount of them get used in South Australia. They're typically used in New South Wales and Victoria, where they have more stable soil, because there are limitations on the size of the beams that can be used in that scenario. But it is a very efficient use of concrete, because what we're doing is we're spreading the support, instead of spreading the support into large pieces far apart, we're getting the support into smaller sections in a more even fashion. So we can decrease the amount of concrete required and decrease the size of the reinforcement required. So that's our waffle pod. Village raft, that's like our normal raft slab. So we've got our normal raft slab like this. That's our cross section we'll get very familiar with. To make that a village raft, that simply refers to having exceptionally deep beams on that raft slab. That's for your very reactive areas like Newton, Ross, Trevor, Athelston, that sort of area where there is a lot of reactivity in soil. And also strip footing. So that's the old, inner city or inner metropolitan area old stone house scenario. Well, a lot of the old stone houses in the inner suburbs didn't actually have concrete strip footings; they had bluestone underneath. But for our strip footings, we typically have, that's a cross section, a cast concrete beam is reinforcing in there, and then the wall is built on top of that. Because that's not locked into a slab to form a raft, it doesn't deal very well with a lot of soil movement. If we get some soil movement straight under that, like that, is our floor. We get rotation in this fashion here of that wall wanting to go up, and also in an elevation scenario, we get a force like that underneath. It's much easier to bend that footing or to crack that footing than if it was part of a large raft that simply moved as one. So slab on ground, referred to as a raft slab. It's got integral beams. So yeah, stiffened raft, stiffened with integral beams and edge beams. What do we say? Construction process is similar. Alright, okay. Yeah. So our process is, first of all, clear the site. It says remove 150 millimetres of topsoil. That's just a bit of a rule of thumb. It may be more, it may be less. Typically it'll be more. So topsoil contains compressible organic matter, so remove to an area of 1 metre around the building perimeter. The reason we remove that soil to 1 metre around the building perimeter is to give a working area for all the formwork, etc. Then we bring in fill. So we take that soil, and we don't have to get rid of that soil. That soil can get stored further back on the site for use in gardens, etc. It's good soil with organic matter in it, and topsoil takes many thousands of years to produce. Don't want to waste it. But then we bring in some fill, so stuff that doesn't have any organic matter in it. So material from a quarry that has been large rocks all just smashed up into smaller bits. Several types of fill. So typically it's going to be quarry rubble, and that's compactable rubble. And that compactable rubble has a good mix of larger aggregate, smaller aggregate, and small amounts of very fine silty clay type elements that help bind that rubble together. And with compactable rubble, you can typically get that down, wet it down a bit, and then get a compaction roller over it and get a very hard surface on it. So yeah, by wetting and rolling in 150mm layers. It has to be done in 150mm layers because when we get further down than 150mm, there's not much impact of that roller anymore. So if we just laid it out 400mm thick, wet it down and rolled it at 400mm thick, the top would get very well compacted, but the bottom wouldn't get very well compacted. So we have to do it in thinner layers. And then on top of that, it's good to bring in some quarry sand or dolomite. That's the sand I assume many of you would be familiar with that. So quarry sand, dolomite, crusher fines. Any other names for it anyone can think of? I think that's typically what it's called. But that's this grey material there, which is fairly loose and friable when it's dry. If you add a bit of moisture to that, it stays really quite stable and can be shaped very nicely. So you can get a very smooth surface on that, and then when you cut your footing beams, you get very neat edges happening. So that's our crusher dust or crusher fines, quarry rubble, wet it down, and then excavate it. So you get some very neat beams. That is the scenario we want for our footing beams. Nice, neat trenches with neat crusher dust on the top. Makes it very simple to estimate the quantities of concrete required, because we don't have to allow as much for variance, and it's going to be very efficient with our use of concrete as well, because we're not just pouring concrete into areas where it's not needed. All the concrete is directed to where it's needed. Trenches such as this are not so desirable, so that's where you've got a fairly collapsible soil, and the excavator has a lot of difficulty doing nice, neat trenches. So you're getting lots of chunks falling out, etc., and lots of variation. Because those beams will still have to be minimum depth and minimum width, it just means you're going to have to allow for more variation in your concrete usage. So you order more concrete to fill in all these little holes and things like that. So less efficient use of your concrete. So in setting out an excavation, set out using string lines at the edge, excavate the trenches, excavate set down areas, and organise engineer's inspection. So the engineer will want to have a look at those beams to see how well they're formed, to see that they're the right size, right depth, etc. Because when that's full of concrete, nobody knows, really. Set down areas, that's for where you have bathrooms, etc., where you're going to be producing a slope on the floor. The way we produce a slope on the floor is by we've got our concrete slab like that, and there's our edge beam, etc. For our bathroom, we'll create typically a 50mm set down in the slab, and we've got our floor trap here. That's our water collected from the floor. So we want to create a slope toward those drains. So the way that is done is you have a set down in your slab, and then you fill this later with a cementitious screed, and then you stick all your tiles on the top with your tile adhesive. So you get that, so that slope is attained later on. That's typically done by the tiler. So you do the screed, and then you do the waterproofing, and then you do the tiles on that. So you've done an excavation for beams. At that time, you also do excavation for your pipe work, and then all that excavation is once again filled in, because we don't want concrete directly on top of those pipes. Actually, yeah, you mentioned before about the lagging of pipes. Yeah. So we've been through all that, and horizontal penetrations. Our moisture barrier, so 0.2mm thick moisture barrier is laid down to stop the wicking of moisture through the slab. It says lapped and taped at 200mm minimum overlaps. There's a bit of conjecture around that. So the Australian standard does not say that you need to lap and tape. It just says you need, it says you need to lap 200mm, but it says you don't need to tape. But many engineers specify that it needs to be taped. So it all depends on who you're working for, but your legal requirements are not that that it doesn't need to be taped. Have you struck that at all?
Yeah, I have seen most of the sites that tape it.
Yes, yeah. I think. Yeah. Did we have that discussion previously as well? Or no, we didn't. No, it's just the lagging.
No, this is
just the lagging that we covered. Yeah. So reinforcement fixed into trenches, tied into a cage, and lowered into trenches. So that's our steel bars. Can anybody, so out of compression and tension, can anybody tell me what the steel bars provide resistance to? What are they really good in? What would they be better? So we've got concrete and steel working together. The reason that we join concrete and steel together is because concrete is fantastic in compression. On that concrete column, I can put a huge amount of weight on that concrete column and it's not going to compress very much. But if I try to lift the building by that concrete column, so got some crazy ass crane, attach that, I'll just snap that column off. If there's no steel reinforcing in there, concrete doesn't work very well in tension. So it's fantastic in compression, not very good in tension. Steel is a bit the opposite. Steel works fantastically in tension. So if I want to lift the building, I'd lift it by that steel column over there, because that steel column will take a huge amount of load before it gives way, before it snaps or yields. So our steel work within our footings, that provides the resistance to tension, while the concrete provides the resistance to compression. Just quickly, I'll draw up very simply a beam. So this is let's say for all intents and purposes, this is a concrete beam. And I have got a really large load happening on that concrete beam. I've got 2 points of support either end, like that. So that beam is going to deflect in this fashion, like that. When we have that beam deflect in that fashion, so it's going like this, this bit here is under tension, and that section there is under compression. So our beam is doing this. This top bit of the beam is getting pushed together. The top bit of that beam is being pulled apart. So with our actions of tension and compression there, we want to have some steel through here to take that tension, and we want concrete up there to take that compression. Now, with our footing beams, it's not always as simple as we've got forces happening downwards. Sometimes we've got forces happening upwards, creating bending like this in various different scenarios. So in this instance, we'll have tension over that portion, and so we want steel to retain that tension there. So that's why we marry those two components together, the steel and the concrete, to provide us some compression, or resistance to compression and tension. We will want to ensure that the house is protected from termites, and there are several ways in which to do this. One way is to just spray down the whole site with a poison, so that any termites that come into the soil will be killed. It's not always a desirable approach, because there are certainly side effects and flow-on effects for general ecology in doing that, and also human health. Although many of the more harmful poisons are no longer allowed, which is a good thing. So we want to ensure that termites can't get into the house. Another way of doing that is sealing up around the pipes. So where we have pipes that go through a slab, because concrete, when it goes off, when it hardens, it loses moisture and will shrink as a result of that loss of moisture. So So our concrete starts as a slab, it's got a pipe going through. That concrete will shrink away from that pipe ever so slightly, a couple millimetres. That will give an avenue for termites to go past that pipe, and the termites are in the house, they get to the timber work, etc. So a way of ensuring that doesn't happen is to have a stainless steel mesh like this fixed around the pipes, and it's really low-tech stuff. Pretty much, yeah, it's that stainless steel mesh, and then it's fixed on there with a hose clamp. So the same sort of hose clamp you use on a radiator hose in a car, something like that. Same sort of thing. So it's just fixed on there, fixed nice and tight, so termites can't get past it. And it covers that area where the concrete might shrink away from the pipe. So termites can't just follow along the outside of the pipe and then into the house. So here are some examples of footing beams. So here we have a host of well, there'd be probably 16mm deformed bars, and then fairly deep trenches. So that's for fairly reactive soil, fairly reactive site. So our steel members there, and then they're all joined together with ligatures. So that's these thinner steel pieces to ensure that they'll stay in the right location. So there we have a series of pipes, and from this we can see we've got what looks to be a 100mm diameter pipe up here. It's going to be for a toilet. We've got a 40mm pipe there. That's probably for a hand basin. We've got a 65 here, either for a toilet or floor truck. I reckon that's for a shower or floor truck. I reckon it's for a shower. And then what looks like to be a 40mm here, that might be for the vanity outside of the bathroom. This larger pipe there, I'm not sure. That might actually be for another toilet. I'm not quite sure the size of that one. But when we arrive at a site, we can typically see where things are going to go from the size of the pipes around. So timber or steel forms are used to form the slab edge, and also used to form set downs and rebates. So I mentioned set downs previously for our wet areas, so we'll end up having a set down happening over here for these areas, so we can create a slope on the floor. But we also have to form rebates as well. And rebates are don't have to draw it again. This is what's known as the rebate. So that's our slab there. This is where our brickwork is going to go. Our brickwork there. And then our timber framing is going to go on that portion there, giving something like a 40mm gap between the two. Typically our rebate there is 86mm, which is the height of a brick plus a mortar joint for under that brick. So that's our rebate. The formwork, typically it's created with using a product called form ply, which is a very strong plywood that has a very smooth surface on that plywood. And it's oiled to allow separation from the slab. So once the concrete is poured, you get that lovely smooth surface and the formwork comes away. Staked and placed sufficiently to resist concrete pressure from the pour. So during the pouring process, there's a fair bit of pressure behind that. We want to ensure that the formwork doesn't blow out and doesn't fall over. If that were to happen, well, that's very disastrous during a pour. It's hectic enough as it is. So when we go to place the concrete, the council want to have advice that we're doing that, so that they can come and inspect the trenches and steelwork prior to concrete going over the top, because once the concrete goes over top, nobody knows what was in there. But they also may want to be there for the concrete pour as well, to see that all that steelwork is still included. So 1 day's notice to council and engineers for inspection. Concrete placement is a continuous process. Placed, vibrated and screeded. Screeded using timber or metal boards in a chopping motion to assist compaction.
Are they always meant to be, are the council always meant to be there prior to the start being poured?
The council are always meant to be notified.
Okay.
So
they can choose not to come?
Exactly, they can choose not to come, yeah. Okay. And I think, actually, no, I won't comment on that, but yeah.
No, most of the council, I have seen their inspectors.
Yeah, so
they also come for the inspections.
Yeah.
Sometimes it doesn't come, but most of the time I've seen on the sites, the inspectors.
But it says when you get your development approval, there's a list of conditions, and typically it's listed in those conditions to say that notification to council has to be made at these stages for these things. So placed, vibrated and screeded using timber or metal boards in chopping motion to assist compaction. So that's a bit of the old school way of doing it. So that's your, many of you may have seen large aluminium screeds, a big long aluminium bar with a handle on top, and you do this to move the concrete around. There are also motorised screeds or power screeds now as well. It's got a little motor on the top just to provide vibration. You just drag it around much quicker and easier. Isolated pads can be used to achieve correct level, and use a laser level for doing that. So laser level has been fairly revolutionary in the whole construction process. Enables that setting out of concrete much easier as well, because you could just set areas and then trowel those off and go, okay, that's exactly the height that we're going for. We're going for those heights everywhere. Gives you a guide for the concrete placement. Concrete is then compacted using a vibrator at every 500mm intervals until water and bubbles stop rising to the surface. So the concrete vibrator, that's a pretty simple tool. It's a 2-stroke motor or a motor with a flexible shaft and a vibrating rod at the end, which is shoved into the concrete as it's poured to just vibrate all that concrete down around the formwork and the reinforcing and bring all the air bubbles to the surface. So the finishing of the slab, that's determined by its use. So it's screeded for tiles and troweled for vinyl or carpet, or it may have extended troweling done for an exposed or smooth concrete finish as well. So has anybody ever noticed the floors in a new Bunnings warehouse? Taken notice of that? Very nice concrete work going into it. They have basically a polished concrete which hasn't been cut back. So it's just produced. Do we have an image of that? Yeah, produced by one of these things. So a motorised trowel or a helicopter, and that scoots along the top. So that's the hand-driven helicopter. You hire one of those from probably any hiring place. And that's typically how a lot of it's done, and they're quite easy to drive. Just sort of tilt them one way or the other, and they scoot around like this. And that trails down and pushes all your aggregate down under the surface and brings up a slurry right to the top. And you do that when the concrete is already relatively hard. So it's at just the right time that is still able to move the concrete around and push it around a bit, but the concrete's not soft enough for it to be ripping up chunks and throwing them around the place. So it takes a bit of, I guess, it's a bit of an art to know exactly when to get the helicopter on there, but when the concrete's fairly firm. This one is one of your larger ride-on ones, and so that trowels a lot more. That covers a far greater distance. And so take note of this. Yeah, next time you go to a fairly new Bunnings, have a look at the floor. They get it very well. Here at the TAFE, being sort of an industrial property which has been brought up to spec, the floors, like they've done similar sort of process in many areas around here, but it's not nearly to the same extent. Nearly to the same sort of quality that you get from in the Bunnings warehouses. But with those ones, they actually get what do we call it, a cement-rich slurry. So they're using a higher concentration of cement powder right on the surface and working that in. So they get a higher MPa, so higher so megapascals of resistance or higher strength right at the top of that concrete, and also very smooth finish, like it's been cut back and polished. So the finishing of slab is determined by its use. Don't use dryers and cause deterioration of the surface. Well, that's all very specific to the people laying the concrete and their expertise, etc. There's a lot of art and science which goes into it, far beyond, I guess, what we're going to cover ourselves. So finishing should be done when a suitable hardness is reached. Floating slab can proceed to produce a surface texture ready for finishing, pushes aggregate beneath the slab surface and closes any cracks. So the first thing that happens, as we said, you get the concrete placed, and you get it placed in just the right areas, and that might be from a concrete pump or just from the straight from the concrete truck, and then it's screeded off, and so we get it from lumps to something within sort of 5 mil variation across that surface with the screed. Following that, you float with a bull float, so that's a large steel trowel on a very long pole. So we get that sort of 5 mil variation with the screed, and then we're down to 1 or 2 mil variation with our bull float. So that's pushing across like this when the concrete is still quite soft and plastic, working it in, getting things very level and getting the aggregate down, and then finally troweling off that surface. So that's getting it to within very little variation. So that happens when the concrete is much harder and can support a trowel on the top. Sometimes the concrete is finished by a wood trowel. So a wood trowel that gives a fairly rough surface because it sort of adheres to the water, has a bit of suction, and creates all these tiny little peaks. Has anybody seen wooden troweled concrete before? You may have seen it on older footpaths. So the footpaths that have just gone in down here near the car park, I think, well, it's not acid etch, but I think the way they do that is they wash the surface to expose some of the firmer aggregate to give a rougher texture. That's not wooden trowel, but
it's sort of lightly lumpy, and then they smooth off the edges, like they run the smoother around. About that wide.
Yeah.
But yeah, it's sort of like it's just rough surface.
No, I'm struggling to give a better definition than that as well. But exactly, yeah. So it's those concrete paths. Let's say we've got a section of path like this, and then you have this 40mm edge done with your edging tool like that. So you do the wooden trowel first, and you just get all these tiny little peaks and whatever. Does that look at all familiar? Yeah, and that edging. The reason we do edging is I'll draw our footpath in cross section like that. So that's a corner which hasn't been edged with the edging tool. That's one that has, and we'll typically get like a little bit of a peak there like that. The edging tool creates a rounded corner there because what we don't want is, because those corners are fairly vulnerable and they'll crack off and split. So if we produce a rounded corner on there, it's a very strong corner and it's not susceptible to looking ugly very quickly. And that edging tool is something about the size of this, and it's just this curved piece that you run inside the edge of the formwork, and it produces that curved edge. But yeah, typically used in conjunction with that wooden trowel. So we've got our bumpier concrete there, and then our smooth edges. So here's some examples of some set downs happening. So set down during the concrete pour, and they've started at that portion because that's the more difficult, involved portion to create. So they get that level correct and then set out some timber formwork, just timber beams on edge, and then they can pour higher around that. So they're set down sorted, and then they start placing concrete in other areas. And then that is that scenario once the boards have been pulled away. So we have this area of our concrete slab which is lower. Yeah. So once again we've got some pipe work there. We can see what's going what's going where. And in this particular scenario, we've got a set down within a set down, so a set down for the shower. So that's going to be a tiled shower base. So once again, several set downs happening here. Set down for bathroom, so toilet, hand basin, floor trap. But then also a set down for the carport area. I assume it's a carport because it is set down. So that carport is going to be open to the weather. We're going to have rain coming in there. If it were an enclosed garage, we would not always necessarily need a set down for it. Very important in the management of concrete is the curing. So we mentioned that last week, or sorry, not last week, the week before. So controlling the loss of moisture from concrete after it's placed. If concrete is not cured properly, it will dry out too fast and produce a loss of compressive strength and poor durability. So methods to cover that curing is cover with sheets of plastic, spray with water periodically, or use a curing compound. So the curing compound sprays on the top, it seals that, or helps to seal that moisture in, retards that moisture loss, and gets a stronger concrete produced as a result. So here's some details around a stiffened raft slab. One thing of note, there's a couple odd sizes happening in there. So that size, that's very common. So 86mm set down, we've got 76mm of brick plus 10mm mortar gap. These sizes are a little bit odd though. We've got 340 width beam and a 260 width beam. Yeah, Abdul, actually you've probably got a bit more experience in slabs and so on. Do you ever see dimensions like that?
No, we use sometimes 200,
Yeah.
250 and maximum 300. In some cases, if there are townhouses, in that case we make 350, not more than that. Even the small houses, single houses, even it is 200 whenever there is a grillage raft.
Yeah.
Raft foundations, then we use even the 200 width.
Yeah. Yeah. But the important thing about that is the widths you're calling out there are very standard sort of widths. So we're talking widths like 200, 250, 300, etc. So we'll get excavator buckets size.
That's
Yes, yeah. So it's determined by the available size of the buckets of an excavator. You don't typically you don't get an excavator bucket which is 340mm or one that's 260 or so. Not that specific. So some odd sizes there with that. But beyond that, that's a detail which you will get to know very well. So we've got our natural soil happening there, our compacted fill brought in there. These are our reinforcing bars that run through the beams, and our ligatures that bind them together. And this is what's called, well, it's our fabric mesh. Yeah.
40
Yeah. Yeah. What's that?
40
no, sorry, that's not 40 up here. That's, well, it's typically referred to as fabric, but it's not fabric like, you know, like the general layman's terminology of fabric is. It's actually a steel mesh that stops the shrinkage of the concrete. So I'm sure you'll know it when I said it. Actually, maybe we've got some pictures of it happening in here. So this here, that's what we refer to as fabric. So that's the steel mesh that goes inside a slab at the top. The reason, or the main reason for the introduction of that steel mesh at the top is to control shrinkage of the concrete. So as I mentioned before, concrete, as it dries out, it shrinks because it loses moisture and pulls in together. That mesh makes that happen in a consistent fashion. Or at times, we use mesh and then imply control joints where we cut every second wire in the mesh to ensure that all the shrinkage happens at exactly that point there. So you with your slab there, got your mesh coming through, snip it there like that, but then also put a groove in the concrete at that point there. Or that can be done with our tool when the concrete's still malleable, or it can be done with a concrete saw afterwards. So you put in a groove like that, and then the concrete will crack at that position. The reason we want to impose a crack is because we can be fairly certain that a crack is going to happen in the concrete, and we want to be sure that we dictate where that crack is going to happen, not the concrete. So, because if we don't put that crack there, we just continue the mesh all the way through uncut, we might get a crack here, we might get a crack there, where we don't want it. Whereas, you know, see, that might be in a bathroom or something like that. Whereas if we say, okay, that's where we want the crack, we can do that. Or when it's large sheds, etc., you line those cracks up with your columns, so things aren't cracking in between where the columns are supported. So that's our typical footing beam detail and our slab mesh at the top. Comes in sizes of SL72, SL82, SL92. So the smaller numbers are for...
Yeah, I have one question here.
Yes?
Why they are called 72? What is the reason that length? You know about that?
No, you caught me out. I can't remember, and I was just trying to remember it. Don't quote me on it. I think it relates to the number of steel bars within a square. So no, actually no, it doesn't.
Because the bar, like I have seen at the sides, the 72 is the thinner.
Yes.
And 92 is a bit thicker.
Yes, it is.
But I will search the answer. I will
It'll take 30 seconds to Google it. But no, I can't remember. But typically, SL72 is for lighter grade slabs, your thin slabs, and your carports, and for paths, things like that. SL82 is for your slabs, and SL92 is for your industrial slabs, for your much larger or thicker slabs. So as you get higher number, the mesh is stronger, but I can't remember exactly what those numbers relate to. Some other different sort of alternative cross sections through slabs. So here we've got a slab on a beam, so that's a suspended slab. There we have not a beam but a slab thickening under a load-bearing wall. Once again here, slab thickening for a load-bearing wall. So a couple of details there to have a look at, but these dimensions, that's far more normal. So 300mm width is a far more normal width. to have your beams. What we have happening here. These are details of Hebel. So we've got Hebel blocks, and then there's a steel rod going along transverse through the Hebel to provide tensional strength through the wall sideways. Yeah. So this is the Hebel blocks that don't really get used so much these days, but a very wide set down for that. And is that one? It appears to be Hebel once again as well, where we have a rod going from top to bottom. That rod is cast in to our floor slab with what's called a cog at the end. So when we bend a bar back and have a return, that's referred to as a cog. So a cog on the end of that. So if you're drawing stuff for an engineer, they'll say 50mm cog on the bar. That just relates to how far it returns back that way. And then typically it'll be a starter bar, and then if it's concrete block construction, it'll be a starter bar. With this scenario, its bar goes, reinforcing bar, which goes all the way to the top or tie down, and then that's fixed to a top plate there to tie all the Hebel down. That have such a detail with that construction, because if you simply attached your rafters or trusses to that top section of Hebel, well then you run the risk of ripping that and taking just those top blocks off. So some alternative footing systems: waffle pod, pier and beam, pier and slab, and grillage raft. We'll make our way through those fairly quickly, because many of the things throughout that are fairly similar. So waffle pod, that's, as I said before, styrofoam void formers used to create what would be the slab of a waffle shape. And so we're creating lots of small beams integrated throughout. Doesn't require excavation, just requires levelling of the site. Forms are placed in a grid pattern. Edge boards are used to form slab edges. Saves in concrete and steel over a standard raft slab. The construction sequence is to remove the topsoil, lay underfloor services, so your pipes and electricity, place crushed rock base, place edge formwork, install termite treatment, put down the moisture barrier, lay pod forms in a grid pattern. Those pods are held in place by plastic spacers. Use any reduced height forms, wet areas to form set downs. Sit around cutouts and services, place steel reinforcement and fabric reinforcement, and pour concrete to the slab and finish as per normal. So that's what they're doing here. So they've put down their vapor-proof membrane, and they're just laying out the waffle pods in a series. Then they've got their spaces between all the waffle pods, and they've put their bar chairs on top to carry the mesh. So that's to ensure that the mesh is held up the right edge distance from the bottom of that slab. And you overlap 2 squares of that mesh, and then you lay the concrete on top. What's going on here is they've got a concrete pump with a boom. So that boom that pumps the concrete from the concrete truck, makes placement very, very quick and easy. So
sometimes in waffle board there are piers in some cases.
Yes, yeah.
I have visited just only 2 or 3 sites. They make the waffle board in South Australia, and I've seen that they make the piers to make the foundation more strong and go deep.
Yes, yeah, to lock into some stable soil down underneath. Yeah. Actually, I'd be interested to speak, maybe somebody from, so Geno's specify that way of, yeah, well, I'd be interested to speak to somebody about that because the firm I work for, we didn't do slabs. So because we didn't have the insurance for it, had a chat to one of the engineers about that and how it works, because I've got varying reports on the application of that, or people said various different things. So with our waffle pod slabs, so that's our void formers there like that, our pods, and then we've got our slab poured over the top. And then we can do some piers down under that, so it's very reactive soil, and we want to lock into some soil which is a bit more stable. So that enables, so this soil up here that wants to swell, it can do that because we're locking the slab into some more stable soil, and that soil can just swell around and crush those styrofoam boxes, because once the concrete is poured, the styrofoam boxes are useless. They no longer have a function under there, and the expanding soil can just push up into those areas. So that's the theory behind it. But then I approached an engineer to have a slab designed for a place in a reactive site, and I said, well, what about using waffle pod with piers to achieve that? And they said, no, we don't do that. We can't do that. You can't, do that in too much of a reactive site. So I'd be interested to know in what scenario, to what extent of reactivity you would,
Yeah, but in South Australia it is rare, but I came to know in Victoria and New South Wales it is very common.
Yeah.
So waffle pods are generally used for reactive soil.
No, so they're not typically used for reactive soil. So it's where we only have moderate reactivity that they can be used.
In a house that we had an extension put on, we removed a veranda which had strip footings, and this is probably as deep as you are, so it looked like a swimming pool. When the floor was taken away. The strip footing was left there, and then it was filled, and then waffle pods were used to create a 10 by 4.5 metre extension metre room. So I'm not sure that the soil that would have gone into that hole type thing would have been compacted.
Not sure, but it wasn't a very large hole though. It was only
probably 2 metres by 2 metres by 6.
Okay. Yeah, that's there, but that 2 metre span is not a huge span, and so it had the strip footings down under that.
It had
still.
A strip footing.
And that stayed in place. So essentially, so what they've done is, so waffle pods. So
they've sort of got a pier, like no, it's not a pier because it ran the full length, but they've already got something there.
Yeah, so they have that strip footing. So what we have happening, so this is your house here like that. Don't have that one there anymore, but we do have a pier. Well, actually, it's funny. Waffle pods, the standard size of them are 1200 millimetres. So maybe you can get small ones. Maybe you can get 1 metre waffle pods. So that would put your old strip footing happening under that bit there, like that, and then that slab continues on further out, didn't it?
Yeah.
So what we have happening there is we only have a fairly short span of 2 metres. We've got a suspended slab which is spanning 2 metres, which is not too extraneous. That's not too bizarre as long as it's well supported at that point there. So it's not a massive span, but it's also a continuous span as well because it's going out past this point of loading onto that old strip footing. So that's not too surprising.
That was a load-bearing wall on that other end, so that was fine.
And there was some footing going out under that.
There was strip footing going down.
And that's gone. So that's not too bizarre a scenario. So could expect that you use waffle pod in that scenario. Possibly one of the reasons they used a waffle pod was actually to bring the height of that slab up to something akin to the inside of the house there, because if we had this scenario whereby would have been about 400 mil set down, so you've got the floor of your house and then about 400 mil lower, and then the top of those. Yeah, and that's probably the main reason they went for the waffle pods, is to bring the height of that slab up. Yeah, because otherwise it would be a scenario of they've got the tops of those, and then if they put a 100 mil slab on top of that, you've got 300 millimetre difference between that room and the rest of your house, which is undesirable. Or you'd have to form up some sort of thing that's attached to the top of those footings, and then you'll slab on top of that. It's all pretty messy. Whereas, yeah, waffle pod gives you that height straight away. And they're also, the really good application of them is in flood-prone areas as well. So out around Lewiston, Two Wells, Virginia area where you've got the Gawler River heading through those really flat floodplains. There you need to pick your buildings up off the ground about 400 to 450 millimetres. So a way of doing that is with a waffle pod. It makes it pretty quick and easy to achieve that height. So that's our waffle pod from underneath. Well, that's something like it. That's a void former slab from underneath. Another form of void former. So they're not waffle pods. I can't remember the name of that product. It's not a widely used one. But once again, operating on that same principle of removing concrete from where it's not really needed. So producing air gaps, forming a void, and then dispersing. Well, this essentially creates lots of dispersed piers, lots of tiny dispersed piers, and then the slab goes on top of that. So it's about being efficient with the use of the concrete. So pier and slab. So that's like what Abdullah mentioned with the application of waffle pods in some scenarios, is the use of a slab and then piers underneath to lock into stable soil underneath and keep it like a table essentially. So we're going down to that stable soil, and we've got a slab sitting on top of that. I won't bore through the sequences too much because they're not significantly different. So holes are bored and to require depth using an auger. Circular forms are placed around the holes if we want to pick our piers up, extend them past the ground level. And then that is, then the concrete is poured, and then formwork for our slab is put in place, and then we pour our slab. So just some interesting photographs of bridges. Pier and beam. So as I mentioned previously, so concrete piers and beams are not very common except for in bridge construction, so civil works. But pier and beam is very typical for timber. So we'll have our floor bearers there and our timber posts, and they will locate on top of either concrete pad footings or also concrete piers. So those concrete piers are formed by using an auger. Yes?
As a designer, will you introduce the pier and slab for your client, whether you're building a 0-story or multiple stories?
Yeah, there is an issue when you're going to multiple stories. It depends on the imposed loads on that slab and where those loads are happening. With our pier and slab like this, if we had framework where our major loads kept landing on top of all of our piers, so directly above all of our piers, then there's not an issue. We can put a lot of weight onto that. We can go up several stories or use heavy construction, like large universal beams or so, and impose those loads straight onto the piers. The difficulty we get to is if we're going up several floors, we might have some loads up there, but then our lower floor, the distribution of our load doesn't directly happen over top of a pier, and it might happen in the middle of a slab there, where it's not directly supported. This sort of scenario doesn't work very well for that. What we want in that scenario is a raft slab type of construction. So, but yeah, it depends on how your loads are transferred through, really. And if your loads are transferred through, well then you can go to many stories. That's you'll probably see it in inner city construction of not that there's too much happening now since the hospital, but you get sites which are excavated to quite deep, and then well actually there's a bit of that happening out here. I'm not sure exactly what they're going to be building on that section there, but they're drilling down into the ground using piers and then putting the reinforcing in there, and then there's going to be some huge loads imposed on that. But in building the Maya Centre and the David Jones and so on, they were doing this sort of thing. They were doing piers and then doing slabs, and then the building would go up from that. So yeah, so you can, yeah, with that construction you can go quite high and impose very big loads on it as well. So that's our pier and beam scenario. Now this is a relatively good segue into our exercise. So I'm going to, if you give me 5 minutes, I'll just get organised. If any of you want to go to the toilet, have a quick walk around, 5-minute break or so. That's fine. We'll do that and reconvene at a couple of minutes after 12. I'll just get this camera sorted as well. That's great.
Yeah, well, I need to leave because I have to reach somewhere at 12:30.
That's fine.
I know about most of the things. I'll cover it.
Yeah, that's.
See you after 2 weeks.
Yeah, enjoy. Yeah, have a break. Yeah.
Thank you. Yeah. I might be having some issue with the advocate. I will
Right.
sort it out. I will send you an email if I get an issue for the advocate.
Yes.
Yes. You know.
Yeah. And where are you with that at the AutoCAD? What are you up to?
I haven't seen since 3 weeks. I have the cross now. This week I will try to sit
Oh, okay.
and
Yeah.
read it out. And there's only, I think, 2 or 3 assignments you told me that need to be submitted in June. I will see and I will come back to you.
Yeah. Okay.